Hello everyone, welcome to CSCN 1001 Computer and Network Security. This is Dr. Amr Al-Mogi. I'd like to welcome you to this lecture. In our last lecture, we started discussing different topics. We continued first the discussion of public key cryptography algorithms, and in particular, we went into the Diffie-Hellman algorithm. And we saw how we generate keys. We saw how to exchange a secret key with the Diffie-Hellman algorithm, and we discussed this vulnerability, which is the man-in-the-middle attack. After that, we went into a different topic, which was message authentication. And we said that message authentication is done mainly using two ways. One is a message authentication code, and the other one is hash functions. These are basically two ways to generate what is called an authenticator. And an authenticator is what you use to validate the origin of the message as well as the integrity of its contents. And we discussed also how regular message encryption is not suitable to do message authentication. And we discussed the differences between just having a message authentication code and a digital signature. And this was the last thing that we discussed. We actually started discussing what is a message authentication code. We said that it's a small block of data, a fixed size block that is generated as a function of the message, and it takes a symmetric key. And this block is then concatenated with the message and sent from the sender to the receiver so that the receiver can try to regenerate it from the received message and compare it with the attached message authentication code. If they match, then the message has been validated, meaning that the origin is now authenticated and the integrity of the contents are also verified. Okay. This is not a digital signature in the sense that it doesn't actually serve the objective of non-repudiation. It achieves only integrity and authentication in this case. And we saw actually different ways to use a message authentication code. Okay, we will start by discussing how we generate a MAC and what are the properties of a MAC. We said last time that the MAC is actually a many-to-one function. This is because if you have a MAC algorithm, it takes as input a key, and with the key, it takes also a message, okay? And out comes the fixed size block. If we say that the message has fixed size n, even though the message size can be variable, the message authentication code algorithm doesn't actually put any constraints on the size of the message. And we say that the MAC size is B, so the MAC size is actually fixed. It produces a fixed size block. Typically, you will have n much greater than b, okay? Meaning that there are 2 power n possible combinations, which is greater than 2 power b possible combinations, which means that the function, the MAC function, is not a one-to-one mapping. It's actually a many-to-one mapping, meaning that there are many combinations of the same of the message that can actually result in the same MAC, okay? So you have several messages that may result in the same MAC. So an attacker theoretically can be able to find an alternative message that has the same MAC. If the attacker is able to find this alternative message that has the same MAC, the attacker can then swap these two messages and the receiver would not be able to detect the difference. Okay, you have to note that the two messages that have the same MAC have to be generated with the same key. If you change the key, then the receiver will actually be generating the MAC also with a different key. And so this will not match. You have to actually find two different messages that generate the same MAC using the same key. Otherwise, the attack will not actually be successful. Okay? If you have more than one message that generate the same MAC, this is called a collision. Okay? Collisions are theoretically present in message authentication code. However, if it is a secure message authentication code, then it will become computationally infeasible to find two messages or more that have the same MAC. It has to be very difficult to do that. Obviously, the size of the key and the size of the output of the MAC algorithm, which is B, the number of bits in the output, are a factor in the security of the message authentication code itself. The larger the key and the larger the size of the output block, it becomes more difficult to find these collisions. And so this is what message authentication code algorithms try to do. The algorithm itself should not have predictable weaknesses, meaning that the attacker should not be able to figure out the message if I know the MAC, and should not be able to find an alternative message with the same MAC. Just like any other cryptography algorithm, message authentication code algorithms are vulnerable to either brute force attacks or cryptanalysis attacks. Brute force, we know how to counter it. You increase the size of the output block and you increase the size of the key. The message authentication code algorithm itself should not actually have vulnerabilities that can be exploited in cryptanalysis. And the attacker that attacks a message authentication code algorithm, his objective or her objective would be to find an alternative message that has the same MAC. And so the message authentication code algorithm should not have vulnerabilities that makes this job easier. And these are here two requirements that are very important in this regard. First of all, the message authentication codes, the output of the MAC algorithm, should be uniformly distributed, meaning that there is no pattern that is more likely to occur than the other. Okay, and the MAC should depend equally on all bits of the message. That means if you have an input message, the output should depend equally on all bits of the message. Otherwise, the attacker will know that this part of the message has a larger effect on the output than the others and can actually exploit it to reduce the search space. How would the attacker actually attack a message authentication code algorithm? If it's brute force, then the attacker will be simply trying different combinations, hoping to find another message that has the same MAC. Okay, and if the size of the MAC is b bits, the attack is typically the complexity of the attack is 2 power m. Okay, actually, if we study this claim a little bit in details, let's say in AES, the key has size k, meaning that there are 2 power k possible keys. Okay, if an attacker wishes to brute force the key, the attacker would actually have to try different combinations of the key until they find the right one. Okay, on average, the attacker would have to try half the search space. That's on average, because this is just the laws of luck. So if you try brute force, then some attackers will end up with finding the key quickly, while some other attackers will end up actually going through the entire space. On average, an attacker would actually have to search through half the key space in order to find the right key. So if the key space is 2 power k, the attacker would actually have to search through 2 power k over 2, which is 2 power k minus 1. This is the complexity of a brute force attack on the key. Okay. In the message authentication code, if the output has a size m bits, then then there are 2 power m possible combinations of the MAC, and so in the message authentication code, the attacker would actually have to go through approximately 2 power m possible combinations to find 2 messages that have the same code. All right, now we move on to how can we actually generate a message authentication code, and how can we do the authentication based on that. Okay. We will discuss several algorithms to generate a message authentication code, but one of the most important ways to actually generate a message authentication code is what are called the hash functions. And hash functions, their job is not just to generate a message authentication code. They actually have many, many uses in cryptography applications and security in general. Just like a message authentication code, a hash function will condense an arbitrary message to a fixed size block, meaning that the hash function, you give it a message and there is no restriction on the size of the message. It produces a fixed size hash that is a function of the message. So the output of the hash function has a fixed size, and the input can be any number of bits. Okay? The difference between the hash function and the message authentication code is that the hash function does not take a key. So the hash function is something that is not keyed. You can actually give it input, it produces output. In addition, the hash function itself is public. So anyone can actually know its details, and it doesn't depend on the key. And so if you have a message, you can actually pass it to the hash function and determine the hash easily. So the output of a hash function for a certain message is not a secret because there is no key. anyone can actually determine the hash of any message given that they know which algorithm is being used. Okay, so this is not how a hash function should be used. Typically speaking, a hash function should not actually be used on its own, and we will see why in a little bit. Okay. So a hash function can be used to generate a message authentication code. It can also be used to generate a digital signature, as we will see in a little bit. This figure here shows different ways that we can actually use a hash function. In part A, we pass the message to the hash function. Out comes the hash of M, and you concatenate that with the message, and you encrypt both. This would be one way to generate a message authentication code. Okay, so here you have an encrypted hash and an encrypted message. Both of them are concatenated together to generate the ciphertext. This is transmitted from sender to receiver. At the receiver, what they will do is that they would reverse the operation in sequence. So the first thing is to decrypt using the same key K. They will obtain the message, they will regenerate its hash, and compare with the hash that has been attached to the message. If they match, then the contents have been verified. This part here achieves the objectives of confidentiality. Why? Because the message itself is encrypted. The message, in addition to the hash, are encrypted. It achieves also the objectives of integrity because I have the hash and I'm able to check the contents of the message, and also authentication. But it does not achieve non-repudiation. Does not achieve non-repudiation because it is symmetric encryption, meaning that the receiver can actually generate a message and claim that it came from the sender. Why? Because the receiver also has the key. Now imagine that the encryption step is not there, meaning that you just generate the hash of the message, you concatenate the hash, and you just send a message. Why then is the hash function not used in this way to guarantee authentication, to guarantee integrity? Won't the receiver be able to actually take the message, regenerate the hash, and check the integrity of the contents? In a perfect world, the answer is yes. However, the problem is if there is an attacker and you did not use a key, so the message is in the clear and the hash is in the clear, the attacker can basically just intercept the message, change any number of bits or change the message altogether, regenerate the new hash of the message, and then just send the message with the new hash to the receiver. Because there is no key in the hash, the receiver will not be able to check that this has happened. The receiver will not be able to verify that this has happened. And because the hash algorithm itself is public, the attacker would know it. The only thing that would prevent the attacker from doing that if a message authentication code is used is the presence of the key. The key is the one that prevents the attacker from being able to do that. And so if there is no encryption step in part A, you just have a message and its hash. The attacker can simply manipulate the message, regenerate the hash because the hash algorithm is public, send a new message with the matching hash to the receiver. The receiver will actually be able to verify this correctly, and the receiver would be fooled. Another use here in part B is that you take the message, you generate its hash, and then you pass the hash only to an encryption algorithm with a key K. This here is a way to generate a message authentication code. Okay, you concatenate the message with the encrypted hash, and then you send everything to the receiver. At the receiver will take the message, generate the hash, and compare that hash with the decrypted hash. Okay, so the receiver will take the hash that was sent, okay, decrypt it with the key K, generate the hash of the message, and compare the hash of the message with the decrypted hash. Alternatively, the receiver can take the message, generate the hash, encrypt the hash with the key K, and compare the encrypted hash with the one that was sent. Both of them are correct. Actually, if you encrypt the hash rather than decrypt the one that was sent to you, it means you will only need the encryption algorithm, so it saves you a little bit of resources. But both are actually cryptographically correct. This one here in part B does not achieve confidentiality because the message itself is not encrypted. The message is sent in the clear. So this achieves integrity because now you are able to check the contents of the message. It achieves authentication, and that's it. The message itself is public. That means I do not care in this part that the message is secret. Everyone can actually read the message. I only care about checking the validity of its contents and checking the identity of the originator, and I'm able to do that using the hash and the presence of the key K. Also, here, the attacker will not be able to do the attack that I explained in part A. The attacker would not be able to take the message, manipulate some of its content, and generate the new hash. Why? Because now I have an encryption step with the key K. In order for the attacker to succeed in this attack, the attacker would have to manipulate the message, generate the hash, which they will be able to do, but then they will have to encrypt the hash with the key K, and they do not have the key K. So the attacker would end up with a new message M dash, a new hash H dash of M dash, okay? And these two things would match. Okay, the new message will match the new hash. However, this is not the end of the story. The attacker was supposed to generate the encryption using the key K of the new hash, which the attacker would not be able to do. Okay, and so the attacker will not actually succeed in this attack due to the presence of the key. If the attacker is able to obtain the key, then everything is lost. You can actually generate the hash of any message you want and encrypt it and fool the receiver into receiving wrong messages. Okay, again, this part does not actually achieve non-repudiation because only symmetric encryption is actually used, and so the receiver can generate a fake message, generate the hash of it, and encrypt this hash using the key K and claim that this message came from the sender. Another way to do the exact same thing in part B, but without actually using encryption at all, is that instead of actually having encryption using a key K, what you can simply do is take the message and concatenate it with the key. So you take the message and you concatenate it with the key S, and then hash the concatenation of M with the key. So the output of the hash function in this case will be the hash of the M concatenated with the key S. So the output of the hash function in this case will depend on both the message and the key. And so at the receiver, what the receiver will do, that the receiver will take the message, concatenate it with the key again, and obviously because this is a key, it's a symmetric key, it has to be exchanged between the sender and the receiver. The receiver will then generate the hash of the message concatenated with the key and compare it with what was sent. If they match, then the sender must have had the correct key, and it must be that the message was not manipulated on its way. Note here that I did not actually do encryption. I just actually concatenated the message with the key and hashed both. The output of this hash will be a function of the message and the key. So I don't actually need the encryption step that I used in part B. Part C actually has the exact same purpose. So part C also achieves integrity and authentication, but not confidentiality and not non-repudiation. Confidentiality is not achieved because the message is sent in the clear. Non-repudiation is not achieved because also I am using symmetric encryption using the key S. Okay. Part D is exactly the same as part C, sorry, but I add an encryption step after the hash. Okay, so now the message as well as the hash are concatenated together and they are encrypted using the key K. And so at the receiver, the reverse is done. So first the encryption is reversed using the decryption algorithm with the key K. The receiver then will take the message, concatenate it with the key, generate the hash, and compare with what was sent. If they match, then I have validated the identity of the origin and I have verified the contents as well. Part D achieves confidentiality because now I add actually an encryption step, achieves integrity because I have an encrypted hash, and encryption here is done by concatenating the message with the key. And I also have authentication because I am relying on a symmetric key to verify the identity of the origin, but I do not have non-repudiation because I'm using only symmetric encryption. Okay. Note here that in parts C and D, I must concatenate the message with the key before applying it to the hash. I cannot simply concatenate the key after I generate the hash, especially in part C. So I cannot actually concatenate the key here in this part. Why? Because then the key would be in the clear. Then an attacker will just actually be able to obtain the key and do whatever they want. In part D, I can actually do that because there is an additional encryption step. So I can actually generate the hash of the message, and then I can concatenate the key because everything will be encrypted afterwards. These two examples that you see in this slide are now examples of what will happen if we use public key cryptography. So now you have a message, you send the message to the hash function, and after that, you encrypt using the private key of the sender. Okay, so instead of encrypting with a symmetric key K, as in part B, you are encrypting with the private key of the sender, for example, using RSA, and then you send both. This is actually a digital signature. Why? Because the private key is only available at the source. No one else has the private key, not even the receiver. So no one can actually claim to be source A in this case. Only source A would be able to generate this message. And so what would the receiver do? The receiver will take the message, generate the hash, and then decrypt the hash that was sent, the encrypted hash that was sent using the public key of A. This step has to be done this way. If you remember here, we said that we can, in part B, we can either, at the receiver, we can either take the message, generate its hash, and then decrypt the MAC, or we can actually take the message, generate its hash, and then encrypt the hash and compare it with what was sent. This is not an option in part A in this figure. Why? Because you cannot actually take, at the receiver, you cannot take the message, generate its hash, and then encrypt with the private key of the source, because you don't have the private key of the source. The only thing you can do is that you can decrypt what was sent with the public key of the source, which is public and everyone has it. Okay. What security services does this figure achieves? Part A. It does not achieve confidentiality because the message itself is not encrypted. It achieves integrity because I have a hash that I can use to verify the contents. Obviously, it achieves authentication, okay, because I can verify the source. Only the source has this private key, and it achieves also non-repudiation. So now, because I have a digital signature using the private key, I am able to achieve non-repudiation. If I add an encryption step after the encryption with the private key, I can achieve confidentiality as well. Note here that this step is a symmetric encryption using key K. So I have public key cryptography using the private key, and I have symmetric encryption using the key K. So this is confidentiality, integrity, I have authentication, and I have non-repudiation. So finally, I have reached the mode that achieves all security services that we have discussed. Here at the receiver, they will start with decryption with the key K. They will take the message, generate the hash, and then take the encrypted hash that was sent, decrypted with the public key of the source, and then compare the two. If they match, then the message is verified. I don't actually have to use symmetric encryption in this step. I can encrypt alternatively with public key cryptography, and you can think what key will be used here. I would have to use the public key of the receiver, the public key of B. If I encrypt the message concatenated with the encrypted hash with the public key of B, I can actually achieve the same objective. And in this case, the receiver will have to start by decrypting with their own private key. Okay, so this is an alternative thing to do. Okay. So we can see that hash functions are very versatile. They can be used to achieve many objectives and do many things in security. So now we will take a look at how we can actually design a secure hash function. There are a number of requirements for hash functions. This slide here shows just some of the key requirements. Which requirements are important? That actually depends on the application. Later on in the course, we will see blockchains, and we will see that there are additional requirements than the ones that we see in the slide. But the ones that you see in the slide are the most well-known requirements for hash functions in order for them to be used securely in any application. The first requirement says that the hash function can be applied to any sized message M, meaning that the hash function takes as input any message of any size. There is no restriction on the message size. The second requirement says that the hash function should produce a fixed length output edge. So given any arbitrary message size as input, the output size is always fixed. The third requirement is that it is easy to compute the hash of a message for any message. So regardless of the message, regardless of its size, it should be easy to compute the hash of the message. And by easy, we actually mean computationally easy. That means it doesn't take too much time or it doesn't take a lot of computational power. The fourth requirement says that given h, it is infeasible to find x such that h of x is equal to h. It means that the hash function is not reversible. This is called the one-way property, meaning that if you have the hash of the message, it should be infeasible to reverse that to get actually the original message. Okay, this is actually the same thing for the MAC. We said before that the MAC need not be reversible. Actually, it is desired that it is irreversible because in the hash, we don't use a key. So it should not be feasible to reverse the hash in order to find the original message. This would not be something that applications would want. The fifth requirement says that given x, it is infeasible to find y such that h of y equals h of x. This is called the weak collision resistance. What it means is that if you start with a message x, okay, and you calculate the hash of this message h of x, it should be infeasible to find a collision. It should be infeasible to find another message that has the same hash. The final requirement says it is infeasible to find any x and y such that h of y equals h of x, and this is called the strong collision resistance. You might think that 5 and 6 are similar. In both cases, I am actually trying to prevent collisions from happening in the hash. The difference between 5 and 6 is that 5 starts with a fixed point, which is the message x, meaning that you have a specific message and you are trying to find a collision for this specific message. So you have a message x, let's say x is a financial transaction or a secret message or something that you want to protect its integrity. This is your fixed starting point. You are trying to find a collision only for this message, okay? And so the fifth requirement says that it is infeasible to find another message y that has the same hash as your message x. In the sixth requirement, it tells you that it is not feasible to find any collisions for any message, okay? So you do not actually have a starting point. You do not have a message that you are trying to find a collision for. You are actually incapable of finding any collisions, any two messages that actually have the same hash. And this is called the strong collision resistance. And this requirement of strong collision resistance makes it increasingly more difficult to design a secure hash function. If you demand that your hash function has strong collision resistance, it becomes much more difficult to design it. Okay? Before we see why, I will actually give you an example of a simple hash function, a ridiculously simple hash function, just to see why it is actually not very easy to design a secure hash function. Let us say that our hash function is just the XOR. So you take as input the message and you divide the message into columns. Okay, so the message is in bits. This column, for example, has 0, 1, 0, 1, 1, whatever. This is 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, and then 1, 0, 1, 1. The simple hash function says is that you take each column and you XOR its values. So this becomes 1, this is 1, this is 0, this is 1, and this is 1. So the hash of this message is 1, okay, 1, 1, 0, 1, 1. Okay. Now, this seems like a very simple hash function. Let's see which of the 6 requirements it can actually achieve. First of all, can the XOR function be applied to any size message? Absolutely, yes. You can actually increase the number of rows in the message, anything you want, and you will still actually be able to apply. Does it actually produce a fixed length output? Yes. The output actually depends on the number of columns, not the number of rows. So regardless of actually the message size, the hash will always be 5 bits in this case. Is it easy to compute? Yes, the XOR function is not computationally difficult. It is actually easy to compute. Given h, is it infeasible to find x such that h of x is equal to h, the one-way property? Meaning, is the XOR function irreversible? Yes, absolutely. Because you can actually change any bits to ones and zeros or zeros to ones, and you will end up with actually the same hash. You will end up with the same result of the XOR function. And there is no way to tell what was the input. So it is difficult to reverse that. You cannot actually say what number of bits produced 11011, especially that the message size can be anything. So you don't even know the number of rows in the message. Even if you knew the number of rows, you do not know which combinations of ones and zeros produce this exact result. So it also achieves the one-way property. Now, requirements 5 and 6. Given x, is it infeasible to find y such that h of y equals h of x? The answer is no. It is not infeasible. It's actually very easy. Because what I can do is that I can change a 1 to 0 and a 0 to 1, and I will end up actually with the same result of the XOR. So given an original message, I can actually easily find another message that has the exact same hash. And if it is not if it is not weak collision resistance, then it is definitely not strong collision resistance, meaning that I can easily find any two messages that have the same hash. So this XOR function is able to achieve the first four requirements, but cannot achieve weak collision resistance, and accordingly cannot achieve also strong collision resistance. Okay. If you require your hash function to achieve strong collision resistance, as we said, this significantly reduces the it increases the difficulty of designing the hash function. And it significantly reduces the complexity of executing a brute force attack on the hash function. As we said, if you have a hash function that produces an output of m bits, to find a collision, the approximate difficulty is 2 power m. This is actually true for weak collision resistance, meaning that if you have a message x with hash h of x, and you are trying to find y with hash h of y, such that h of x is equal to h of y, the complexity of this attack has actually on the order of 2 power m steps. If you want the function to be strong collision resistance, not weak collision resistance, then actually the complexity of the attack will be reduced to 2 power m over 2. Okay, it's actually a significant reduction in complexity. And the reason is something called a birthday attack. If you remember, I think you probably discussed this in a previous math course. The birthday attack or the birthday paradox says that if you have a number of people, what is actually the minimum number such that there are two people in that group that have the same birthday? And the answer is surprisingly small. It's actually 20, I think it's 23 people. Okay. Many people would think that it is probably a much larger number for us to find a likely couple in that group that have the same birthday. But this birthday paradox, and there is a complete mathematical proof depending on probabilities actually, says that the minimum number of people such that there are two people within that group that have the same birthday is actually 23. The birthday attack is actually extended to hash functions by saying that it is not very difficult to find two messages that actually have the same hash. Okay? The complexity of this attack is reduced to 2 power m over 2 instead of 2 power m. So if you want weak collision resistance, okay, the complexity is 2 power m. if you want strong collision resistance, the complexity is reduced to 2 power m over 2. You have to take care of that when you are choosing the size of the output of your hash. If you want the complexity to be 2 power 56, then you have to choose the output of your hash to be 512, so that when you do 2 power 512 over 2, you end up with the 2 power 256 that you desire. So it significantly increases the required size of the output in order to achieve the desired level of security. So how can the attacker implement the birthday attack on a hash function? Now imagine that someone has a letter, and the letter, for example, includes a financial transaction. The letter actually has a lot of writing, so there is a lot of things there. And in this letter, there is, for example, a financial amount that is exchanged between two people. Someone is actually telling, for example, the bank or someone that I want to transfer this amount of money to someone else. What the attacker would do is that they will take this original message and generate 2 power m over 2 different combinations of this message. These different combinations will have roughly the same meaning as the original message. Something like that. Dear Anthony, this letter is to introduce you to Mr. Alfred. You can replace that to. You can replace that with. I'm writing to introduce to you Mr. Alfred. Okay, so it's manipulation of the message, but it has the same meaning. Okay, and you can generate different combinations. For example, in the first combination, you can do this one and this one together, and in the next combination, you can do this one, but with U2 and not 2U, for example. Okay, and so you can generate a very large number of different combinations using these simple alterations, and they will all actually have the same meaning. So you generate different combinations of the same message. Okay, 2 power m over 2 variations of the valid message. And then you take the message that has the wrong amount, so the fraudulent message. Okay, you take another message that has very, very similar content, except, for example, for the monetary value that is inserted. Okay, and you generate 2 power m over 2 variations of the fraudulent message. So you generate 2 power m over 2 variations of the original message and 2 power m over 2 variations of the fraudulent message. You take the hash of the variations of the original message and you take the hash of the variations of the fraudulent message. There is a 50% chance that you will be able to find two messages in these hashed variations that have actually the same hash. You'll be able to find two variations, one of the fraudulent message and one of the original message, that actually have the same hash. There is a 50% chance that you will be able to find that, according to the birthday paradox. This is why the complexity of the attack on hash functions is reduced to 2 power m over 2 if you desire strong collision resistance. How do you beat it? You just increase the size of the output of the hash function. Okay. This is what we have been saying. And this attack is also possible in the Mac, except that the Mac is a little bit more difficult because you have a key. And so now it becomes a debate whether it is more complicated to attack the output of the Mac itself, which has complexity 2 power m over 2 according to the strong collision resistance requirement, or you attack the size of the key. Okay, but in practice, it is actually the complexity is usually on the order of 2 power m over 2. Okay, now we can start looking at the structure of practical hash algorithms that are used in practice. When we were discussing symmetric algorithms, we said that there is something called an ideal block cipher, where you have a mapping between the input and the output, and the ideal block cipher is something like a decoder. And we said that this ideal block cipher is not practical because the size of the key would be very, very large. And so instead of the ideal block cipher, we rely on blocks of substitution and permutation that achieve confusion and diffusion. Hash algorithms are designed in a different concept. Okay, so to design a practical hash algorithm, you have to have a secure hash function that achieves the objectives of the hash algorithm, the 6 requirements that we said, but you don't use it once. You use it several times in sequence. So you take this hash function and you give it as input an initial value, and unlike the modes of encryption, the initial value here is usually just something fixed. And with the initial value, you give it a block of the message that you're trying to encrypt, that you're trying to hash. The output of that is fed as input to the next step, together with the next block of plain text that you're trying to hash. And you keep repeating that until you hash all the blocks of input, and out comes the hash of the entire message. This is actually how a hash function can take the message of any size. What you do is that you just simply repeat the usage of the hash function, okay, over and over again. And the output of every stage is always a fixed size block. So this CVI is always a fixed size block. You just use the hash function repeatedly until you hash all the message blocks. So if you have a message of a very large size, you divide it into smaller blocks, and you feed each block to a stage in the hash function until you have actually fed all the blocks to the hash function, and out comes a fixed size. Okay. Research has shown that this structure is actually secure, and this is what almost all hash algorithms in practice use. We will actually study only one secure hash algorithm, and it's called SHA, or the secure hash algorithm. This is actually the most prevalent one in practice. There has been several versions of it. SHA 256, meaning that the output of the hash function has 256 bits, was used for a long time. It is now deemed not very secure. And so the one that is used widely now is SHA 512. There used to be something called MD4. It produced 160-bit hash values, and this is now recognized as very insecure, and you can easily find collisions in it. Okay, so what does the secure hash algorithm look like? It looks exactly like the structure that we said. There is an initial value that is fed to a hash function together with one block of the message. And you divide the message into blocks of size 1024. And if the last block is not a multiple 1024 of 1024, you add what are called padding bits. You just actually add dummy values, constant values that are added in the end to fill in the last 1024 blocks. So you feed the initial value together with the first block M1. Out comes a value that you do a modulo addition, an addition modulus 2 power 264 with the input, and this becomes the input to the next stage, H1, together with M2. The output is modulo added to become the output of the next stage, and then this is fed as input to the next stage, and so on, until you end up with the hash code of this message. Again, how many stages do you have? As many as you need to hash the entire message. So the number of stages actually depend on the size of the message. So let us now take a look at what is actually in this round function. It's actually quite a complicated function. It's a function that has itself 80 rounds. So each one of these functions has 80 rounds in them. Basically, as input, you have the initial value, which is 512 bits. You divide it into 8 blocks, each is 64 bits. So these are the blocks A, B, C, D, E, F, G, H. Together, you get a value that is a function of the original message. So you take the original message MI, you pass it through a message schedule, and out comes a 64-bit value that is also input to each round. Something happens in each round. It's identical. I will show it to you in the next slide. And the output of that is fed as input to round 1 and round 2 and so on until round 79. And the output of that is then XORed, modulo added with the initial value. And this becomes HI, which is the input to the next round function. So every time the input to each function changes, because the input to each function is the output of the one before it, the step before it, and the message that is input to it also changes. Okay, but the steps that are done between round 0 and round 79 are obviously the same. And now we open up what is actually inside one round, and it is that. You can see that it is actually a very complicated structure. I will not go into the details of what actually happens inside each round. You can take a look at it yourself. Unlike AES, I will not actually go into these details, but it is sufficient for you to see that the objective that we mentioned before, that you want to make actually the output of the hash function uniformly distributed, meaning that there is no likely patterns in the output, and you want also the output to be dependent on all the input bits. So you can see from this figure that there is a lot of combinations, there is a lot of additions, there is a lot of operations that happen, such that the values of A, B, C, D, E, F, G, H that are output from each round are dependent on all the input values coming in. Okay, and these are actually the mathematical equations that represent what happens in a single round. If you're interested, you can take a look at them yourself. I'm not going to go into their details. Next, we will see one very important algorithm that is used to generate a message authentication code from a hash function. And the algorithm is called the Key Hash Message Authentication Code, or HMAC. HMAC is a very simple algorithm. It says that if you want to generate a MAC using a key K, what you do is you take the message, you concatenate it with the key XORed with a constant value that is called IPAD. Okay? So you take the key, you XOR it with IPAD, and you concatenate that with the message, and you hash the concatenated values. You take the result of this hash, and you concatenate it with the key XORed with another constant, which is called OPAD. OPAD and IPAD are constant values. They do not change in the encryption of any message or with using any key. They're just constant values in the algorithm itself. Okay? So the result is then hashed again, and this becomes the MAC. So HMAC has two steps of hashing. One of them hashes the message concatenated with the key XORed with IPAD, and then the result of that is concatenated with the key XORed with OPAD and hashed again. HMAC doesn't actually specify which hash function should be used. Any hash function should be used, and in fact, the security of HMAC depends on the security of the underlying hash function. So obviously, it is recommended to use SHA in HMAC so that you end up with a secure MAC algorithm. If you use a hash function that is not very secure, you would end up with a MAC that is also not very secure. This is an illustration of the operation. First of all, you take the key, you XOR it with IPAD, and IPAD is the value 36 in hexadecimal. The result of that is concatenated with the message, and as you see here, the message is divided into blocks, just like you would input the message to a hash function. So this concatenation is fed into the hash function, whatever it is. Let's say it's SHA 512, together, of course, with the constant initial value. Out comes the fixed size bits, the n bits. If it's SHA 512, then this will be 512 bits. These 512 bits are then XORed with the key, XORed with OPAD, and OPAD is the value 5C in hexadecimal. This is concatenated with the 512 bits that are here. If you need to do padding, then you do padding. Okay, depending on the size of the key. Also, HMAC doesn't actually specify what is the size of the key. You can choose any size of the key you want. Obviously, the larger the size, the more secure the MAC is. And then you hash again, and out comes the specific value, depending also on the size of the hash. If it's SHA 512, then you will have 512. Okay. This is basically HMAC. Another important way to generate a MAC is actually just from blockchain encryption, cipher blockchaining mode of encryption, which is called cipher-based MAC or CMAC. If you remember blockchaining, what you do is you take each message, you encrypt it, and the encrypted message here, this is the ciphertext of the first block. You take it and you XOR it with the second block, and then you encrypt the result of this XOR, and you keep doing that. What will happen is that the ciphertext in the very last block will depend on the values of all the blocks before it. And so this is actually a good way to authenticate a message. If you want to authenticate a message, you divide it into blocks. You encrypt each block in a chained way. And then in the very last block, you can take a bunch of bits, for example, the most significant 128 bits or something like that, and this becomes your MAC. Why is this a good way to actually generate a MAC? Because this MAC will actually depend on the content of the entire message because of the chaining, and it also will depend on the key. So you have actually your two requirements. It depends on the key and depends also on the size, and it depends on the key and depends also on the chaining itself. Again, you can actually use any size message because you can have any number of stages in the chaining. Okay, and the result always has a fixed block because the result is the most significant number of bits that you require. So it achieves actually all the objectives that you need. Okay, so now we have seen HMAC and CMAC as two different ways to generate a message authentication code. The last thing we will actually look at in message authentication, we will actually revisit modes of encryption. So all the modes of encryption that we have discussed so far, whether it is electronic codebook mode, or cipher block chaining, or cipher feedback, or output feedback, or the counter mode, they are all modes that achieve only the objective of confidentiality, meaning that there is no authentication in all the encryption modes that we have discussed so far. If you want to have a mode of encryption that achieves confidentiality as well as integrity and authentication, this is actually what we will discuss now. This is actually the topic known as authenticated modes of encryption. They are modes of encryption that achieve both confidentiality, just as with the regular encryption mode, and achieves also authentication and integrity. Okay. First one that we will take a look at is something called the counter mode with CBC or CCM. Counter with CBC mode or CCM. Basically, this mode of encryption consists of two parts. A part that achieves authentication and a part that achieves the regular encryption. The regular encryption is basically similar or identical to the counter mode. You take the plain text, you divide it into blocks, and you feed it to the counter mode. So you have a counter. Each time it actually XORed with the message, and you feed it to the encryption block, and that's basically it. So the encryption part is the same. The authentication part is a little bit different. You take the plain text, and together is the association data and a nonce. A nonce is a random value that is used only once. What is the association data? It's actually the header of the message. For example, you have the IP addresses, the MAC addresses, any other headers that you have in the message. You concatenate all of that with the plain text together with a nonce. And this becomes the input to the CMAC algorithm. The CMAC algorithm is the one that we have discussed here. So it's just block chaining, okay? And you take the most significant bits out of it, and this becomes what is called the tag, okay? So you take the plain text, together with the headers of the message, together with the nonce, you feed them into the CMAC algorithm, it produces a tag. Now, you take counter 0, the very first counter, you encrypt it with the key, you take the most significant bits out of them, you XOR it with the tag, and this becomes your authentication data. So you have to take a look here, what is actually authenticated and what is encrypted for confidentiality. Only the plain text passes through the counter mode. So only the plain text is assured confidentiality only. But the plain text and the association data are authenticated. So the plain text and the authentication data are passed into CMAC. The association data is not encrypted with the counter mode because you have to have the headers in the clear. You have to have the IP addresses and the MAC addresses in the clear for the networking devices to do routing and forwarding. So you cannot actually pass them to the counter mode. So this authenticated mode of encryption, which actually is supported by Wi-Fi, allows you to do authentication for all the packet, the entire packet, including the header, while doing encryption only for the actual content of the packet. Okay. At the receiver, you can actually do the same. You can take the plain text part, okay, and pass it to the counter decryption mode to obtain the plain text back. And then you have the decrypted plain text. You concatenate with it the association data, and you concatenate with it the nonce, and you pass it to CMAC. You generate the tag. You do the encryption. You do the decryption with counter mode and the XOR, and you compare it with the tag that was sent. If they match, then the packet is authenticated for integrity and the identity of its origin as well. The last mode that we will discuss is another authenticated mode of encryption that is called the Galois counter mode. And this is also a very popular authentication mode that is also supported by Wi-Fi. The idea here is also that there is a part that is used for authentication and a part that is used for encryption. The encryption part is just the counter mode, okay? This part here. So you have the message, you have the counter that is incremented by 1 in every step, and the result of the encryption of that counter is XORed with the plain text. Just a regular counter mode. For the authentication part, you take the bit sequence all zeros and you encrypt that with the same key. Out comes a block H. In every step, you take the authentication information, which is also the plain text concatenated with the headers, concatenated with the nonce, and you do a binary multiplication with the value H. So the value H, which was the result of the encryption of the pattern zeros with the key K. You do a binary multiplication with H, and you pass the result of this multiplication to the next step. You take as input A2, okay, you XOR it with the output of the previous step, and you do a binary multiplication with H. In every step, you are doing a binary multiplication with H of the XOR between the current block of authentication data and the output of the stage before. You do that for all the data that needs to be authenticated, which is typically the entire plain text concatenated with it, the header and a nonce. After that, you chain it with the ciphertext. So the very last authentication block is then XORed with the ciphertext, and the result is then binary multiplied with the same value H. And you do all of that for all the blocks of ciphertext, and in the very last step, you XOR the length with the result of the last multiplication block, and then you multiply it with H, and you XOR that with the output of the first block of encryption, and this becomes your authentication tag. Okay. So again, you have a packet. Okay, let's say this is your packet. This is your plain text, and these are your headers. Okay, you take the plain text part, okay, and you pass it through the counter mode, just the regular counter mode with all the steps, and produces C1, C2 until Cn. Okay, and then you take the entire thing, the plain text concatenated with the header, okay, and you pass it through the authentication phase together with the output of encrypting the binary bit sequence zeros with the key K. This is H. So in every step, you XOR A1 with the output of the step before it, and you multiply with H. And you keep doing that until you encrypt the entire authentication information, and then you chain that with the output of the encryption part, okay, until you go through the entire blocks of encryption, C1 to Cn, and then you have another stage that includes the length of the packet as the information, and then you XOR it with the first block of encryption, and out comes your authentication tag. Why is it necessary to actually have the length as part of the process? This is because if someone actually drops part of the data or blocks part of your data, you will know that you received the wrong information. You will know that something is wrong because the length of the packet is actually there. So the length of the packet is also authenticated. At the receiver, you can actually do the same thing. You can take the ciphertext blocks, you chain them in counter mode, and you can actually produce the same authentication information from the step. In both modes, you transmit the ciphertext blocks. So C1, C2, up to Cn. These are transmitted by themselves, and the authentication tag is also transmitted. And so given the ciphertext blocks, you can reverse the information, and you have the headers, you can regenerate the authentication tag, and you compare. In the Galois counter mode, you do the same. You transmit C1 to Cn on their own, and you can then use them to decrypt, and you have the header information which you can use to regenerate the authentication tag. Okay. That's it for message authentication, and this then completes the cryptography part of our course. For the rest of the course, we will actually be taking a look at applications of cryptography and security. In the next lecture, we will go into blockchains as an application, and then we will see key distribution, and after that, user authentication, and after that, internet security. We'll talk to you in the next lecture.